Yeah. So let's take a look here.
Quantum mechanics and the shape of atoms as discovered by...
Okay, we need sound. 39. Now, if you find that this guy is talking too quickly, please raise your hand. Okay, I'm going to put up the subtitles because he does speak rather quickly, and we can put it down to 0.75 speed if you prefer. Okay, but we'll start with it at full speed. Let me know if it's too fast. Don't worry about filling anything in at this point, just watch. Okay?
Quantum mechanics and the shape of atoms as...
Okay, we're going to just bring the volume down a little bit.
Discovered by Schrödinger. We all know about quantum mechanics, which is of course the physics theory that describes atoms and elementary particles, how they move around like slushy little waves, and interestingly, it predicts what they look like, what shape they have.
Too fast? We're good? Okay.
It was invented in the first couple of decades of the 20th century by a lot of people all working together. Amongst them were Planck, Heisenberg, Bohr, Davison, du Broglie, Einstein, and of course Schrödinger. These guys already knew a lot about atoms from the scientists who came before them. For instance, they knew that there are about 100 different atoms in nature, and that these atoms join in larger structures such as molecules, metal lattices, and salt lattices to make everything we see around us. But what they didn't know, what exactly was going on the inside of the atom. What it was made of, what shape it has. So they were doing experiments on that. And pretty soon they found out that atoms themselves are composed of smaller particles. They found the proton and the electron, and they were featherizing the neutron. And with the protons and neutrons, they almost immediately knew what the deal was. They realized that they were clumped in a very tiny core at the center of the atom. That core was really small. A typical atom is about 300 picometers across, whereas that core is typically 0.01 picometers.
Okay, so let's put this in perspective. 300 picometers. A pico is 10 to the negative 12. So if we are at 300 picometers, that's 300 times 10 to the negative 12. So if I move my decimal place 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 places over, that's how many meters an atom is across. Okay? And then if we look at our nucleus, the nucleus is going to be 1, 2, 3, 4, 5, 6, 7. And then we have, it is, that's 100, that's 100, 4 more zeros. 1, 2, 3, 4 meters. That's our nucleus. So teeny, 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 tiny, teeny, 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 tiny. Yes?
So this leaves this big open space in an atom, and they realized that this open space was going to be the domain of the electron. But what they didn't know was exactly how the electrons are filling this space. If they are spinning around or orbiting or what. So they made an initial sketch. They called it the planetary model of the atom. Basically the core at the center and the electrons spinning around in big orbits. It was their first idea of what an atom looks like. It proved to be incorrect, but it was a fine enough starting point. It made some very nice predictions, and it allowed them to start doing experiments, and they did. One man who was looking at these experiments was a Frenchman called du Broglie, and he was noticing something very interesting. He found that when electrons were forced to interact with matter, either through some physical process or by hitting a detector, that the electrons presented themselves as particles, as hard little balls of matter. Interact with matter, either through some physical process or by hitting a detector, that the electrons presented themselves as particles, as hard little balls of matter.
And this is how we think about electrons. Yes, we're like, electron, little tiny little ball of matter. Yes? Right? And you can see that if that electron interacts with something, if it smashes into a photon, it can veer off. Just like if we had a pool ball hitting another pool ball, it would veer off. We can have an electron smash into a detector plate and it might make it fluoresce or something like that. It might make it light up a little bit. Okay? That's what particles do when they hit things. They give some energy off and you can detect it. So when electrons are interacting, they are like particles. So far, so good. So far, not weird. Just wait, weird is coming.
Kind of what you expect them to do. But when the electrons were allowed to move on their own, either by being shot through a crystal or allowed to wander through a vacuum, they always propagated as if they were waves.
So, electron going through a crystal, it no longer looks like a particle, it no longer behaves like a particle, it behaves like a wave. Did you guys learn about waves last year?
Yeah.
Yeah? Okay, so you've got light waves, things like that. Electrons are behaving like waves of light or, waves of sound or waves of any sort of wave, okay? How is it a wave and a particle when you do different things to them? When it's interacting, it's a particle. When it's not interacting, it's a wave. This is weird.
It was almost as if when you stop messing around with the electron, it would suddenly fall apart into some sort of wave function. Some sort of probability wave that sloshed around all of space and predicted where the electron was likely next to be found. This was the first time they encountered particle-wave duality in matter, and it spelled disaster for their planetary model. Because this model really assumed that the electron stays a particle during the entire orbit and doesn't fall apart into a wave halfway through. So they needed a new model, but they realized that this model couldn't come from classical mechanics because classical mechanics makes the same assumption that particles stay particles. In fact, they would need entire new mechanics, some new theory that included the wave-like nature of particles. And this is when Schrödinger entered the picture. He had looked at the experiments as well, and he found one common theme running through all of them. In his insight, he saw one law of nature, one equation that seemed to hold no matter what you did. He called it the wave equation.
Now, just in case you're wondering, yes, that was in my first year chemistry textbook, and it scared the snot out of me. I was like, what is that? Ah! Anyway, we didn't actually have to work with it, but it really terrified me. There were so many letters that I didn't know, Greek letters. Anyway, there we are. Oh.
Equation, he was now in a very interesting position. What he could do is take an atom, any atom, take its properties, stuff like its mass and its charge, all those numbers, put that in that equation, do the math on it, and what he would end up with would be a series of pictures that showed what that atom looks like. He went on and did it for hydrogen, which is the easiest atom. It's just one proton, one electron.
He's doing the easiest atom right now.
And that one proved to be crucial into unlocking the shapes of all the other atoms. And when he had worked his way through the math, these are the pictures he found. Ladies and gentlemen, the shapes of hydrogen. So you remember those crazy hyperactive flies zooming about? Well, they don't all make spheres. Some of them make a couple of teardrops. Okay, they're drawn a little differently here. Some of them make like a donut with a balloon on the top and a balloon on the bottom. You get sort of like a 4 balloon shape. You get all kinds of crazy shapes. And that is the space that an electron occupies. Okay? So if you look at an electron, if you detect it, if you interact with it, it's going to be a particle somewhere in that space. But if you're not interacting with it,
It simply is that region. It's not in that region, it is that shape. It is a wave that makes that shape. And if you're like, what? Then you're thinking correctly. Okay? At this point in your lives, and at my point in my life, this makes me say, what? Okay?
This then is how an electron fills the empty space in an atom, not by spinning around, but instead with its blobby-shaped wave function, which we call the orbital. What I've drawn here each time is just the same hydrogen atom with a proton at the center, and the electron has been allowed to go into a different orbital each time by giving it energy, for instance.
So don't worry about these like little things, the 2px, that's just the name of the orbital, and we don't need to know those. In fact, this model, you need to know very, very little about it, just that it exists and that it is a little bit bizarre, okay?
And if you look at this one, these three blobs together form that one orbital. They house that one single electron. And this one makes a fine example. We can look a bit at its properties. What you can do in an experiment is take a hydrogen atom and prepare it in this orbital by giving it some energy, for instance. And if you leave it undisturbed, then the electron takes this shape. It becomes this wave function, this blobby shape. And if you then were to take a measurement of the electron, find out where it actually is, what would happen is this wave function suddenly collapses. It condenses into a single point, which we call the electron.
Okay, so undisturbed, we just have this shape. If we measure it, all of a sudden, it's no longer this blobby shape, but it is somewhere in that blobby shape. Okay?
If you then were to re-prepare your hydrogen atom in the same orbital, maybe give it some new energy, then you can do a new measurement, and you can find that electron in the same blob, or in any of the other blobs. And if you were to repeat this thousands of times, you would end up with a picture very much like this. Notice that there's a higher probability of encountering the electron at the center of a blob. There the probability wave function becomes more dense.
Okay, so this is like a time-lapse guys. This is like time-lapse photography. So if you like took these measurements thousands and thousands of times, you would see that the electron is most often in the center of a blob. And as you get further from the center of the blob, it spends less time far out here. And then it doesn't spend hardly any time out here. Although in theory, that electron can actually be on the other side of the universe. Isn't that fun? Very unlikely, but it could be.
But there's something interesting about these pictures, of course, something that is, well, staring us in the face. The fact that these blobs are not connected. There's an area in between where you cannot encounter the electron. So it kind of begs the question, how on earth is the electron traveling from one blob to another? Is it teleporting or what? This was one of the important questions that led to 40 years of heated debate that ended up with Einstein saying very angry things about dyes.
So, Einstein did not like this. So, if Einstein, with his big, huge, mongus brain, was like, yeah, then it's okay for us to be, yeah, yes? So if you're like, I don't know, it's okay. It's all right. Okay? After years and years of having taught this, I feel comfortable with my nya, okay? It doesn't feel uncomfortable for me anymore. I don't understand it, but I feel comfortable with my non-understanding, okay?
But who cares? Schrödinger had made an important discovery. He had found the shapes of hydrogen. And using that as a basis, those that came after him were able to find the shapes of all the other atoms. They are very much based on hydrogen. They use the same orbitals. It's just that the higher atoms consist of more electrons, therefore they require more orbitals to house all of them. So you end up with a situation where the orbitals all get stacked on top of one another, overlapping but not mixing. They do, however, repel, because that's what electrons do, they repel one another. So the orbitals begin distorting each other according to some very complicated math. But these guys were also good at what they were doing. And, combined with Schrödinger's discovery, they had now made a link between physics and chemistry. A link which in fact led to an entire revolution in both of them.
Okay, so you can see we have, what do we have? We have MRIs. could not do this without quantum mechanics. We have electron microscopes, string theory, diodes, molecular design, quantum, electrodynamics, transistors, interstellar spectroscopy, and rocket fuel. So you could not have any of these things without quantum physics, okay, quantum mechanics.
So with that, I would like to conclude by just saying, Mr. Schrödinger, thank you very much.
Okay, so that's just an introduction to the wild, wild world of quantum mechanics for you. Like I said, you don't need to know much about it. If you take Chemistry 11 Enriched, you'll get a deeper flavor of it. If you take regular chemistry, you won't see this until university, okay? So, but I know there are some of you who are interested in that pathway, so it's nice for you to have seen it and be like, wow, yeah, electrons, they be weird, weird little guys, all right? But let's go back to some more grounded stuff, some more concrete, lovely little things, and you guys can work on your homework, which would be page 73, number 2 and 3. And page 75, number 4. We have 10 minutes, 15 minutes, and page 76. So anywhere between pages 73 and 76, if there's a question, do it, other than number 5.
Can I go to the bathroom?
Yes.